A modern arch bridge holds thousands of tons of concrete and steel, plus the weight of fast-moving traffic, suspended in midair by slender cables. To keep that structure standing, engineers have to account for two distinct types of weight. The first is the static load. You see this in standard office buildings, which primarily hold up their own resting weight against the pull of gravity. A vehicular bridge operates as a giant machine. Every time a fully loaded transport truck rolls across the deck, it sends a massive pulse of energy, a dynamic load, radiating through the entire structure. That repetitive wave of stress triggers fatigue. As standard steel is pounded by millions of loading cycles over the years, the constant flexing causes microscopic fractures to form and expand deep within the metal. Without highly specialized tension members designed specifically to absorb this relentless punishment, the constant motion of daily traffic would eventually tear the bridge apart. ASDO structural tie bars were developed to handle these extreme dynamic forces safely. This technical data shows the system's capacity, with sizes ranging up to an M160 diameter. These bars are certified to handle design resistance loads of up to 9,600 kilonewtons. The physical anchor point between the bridge and the tie rod relies on these specialized cast steel clevicens, known as fork connectors. This heat map illustrates a finite element method design in action. The tension forces are distributed homogeneously across the connection plates, preventing the localized stress that leads to structural failure. However, securing the physical connection is only the first half of the problem. The structural rod itself must still survive the internal friction created by constant motion. Longevity in this system starts with how the threads are formed. While standard bolts use cut threads, these structural bars use cold-rolled threads. This comparison shows why. Cutting threads into metal severs and weakens internal grains. The rolling process presses steel into shape, maintaining a continuous grain flow for vastly superior fatigue resistance. In testing, these systems survived over 2 million loading cycles without failing. Even with perfectly manufactured fatigue-resistant bars, the installation requires precise tuning once the components are attached to the bridge. Engineers use specialized hydraulic rigs on site for a process called in situ stressing. This allows them to measure and adjust the exact tensile load that each individual bar carries. Tuning this tension in real time ensures the load is distributed across the bridge deck as intended. This prevents any single rod from carrying a disproportionate, potentially lethal amount of stress. Beyond the physics of the bridge, these projects depend on logistics. To bypass this bottleneck, ASDO 355 IS tie rods are manufactured locally, directly in India. This chart compares the timelines. By eliminating international heavy steel freight, localized manufacturing provides a rapid delivery cycle that keeps the construction site moving. This also ensures crucial on-the-ground support. Partners like Bolin Ventures provide hands-on assistance during both the design phase and the technical in-situ stressing process. Combining European engineering standards with localized manufacturing allows for the creation of architecturally stunning, fatigue-resistant bridges that stay on schedule.